Hello friends, welcome to Knowledge Galaxy to rediscover the basics with Mayank Tiwari, a premier coaching and training channel dedicated to metallurgy studies and consultancy. Established to cater the needs of students, degree, diploma and AM/IIM metallurgy, competitive and recruitment exams for GATE, SAIL and various other government and private sector companies, metallurgical industries, working and aspiring professionals and whosoever seeking knowledge and information about various subjects and topics of metallurgy, ferroalloys, operational process optimization, productivity improvement analysis, etc. To impart practical industrial knowledge as per your specific requirements via tailor-made training sessions for your colleagues, employees and students, please contact me on knowledgegalaxy26@gmail.com or WhatsApp me on +91 99 071 44101 for scheduling and organizing the sessions at your place or via video conferencing. My dear friends, nowadays technology has improved so much that actual physical distance doesn't matter anymore. You can get all your doubts cleared by sitting at your home, at your comfort zone, just by contacting me over WhatsApp or phone, so that for your benefit, please do contact me for any of your doubts. My dear friends, I have made so many videos which are available on my YouTube channel. So I request you to visit my channel regularly and repeatedly and watch all the videos available there so that you can gain maximum knowledge about the subject and topics, and also request you to watch all my videos from start to finish so that you can gain the maximum and complete knowledge about the topic. My dear friends, as you know that training is costly, but not to train is still costlier. And when you are not having complete knowledge or don't get any information about the topic which you need to know, so you can contact me. If you don't find anyone who can help you to clear your doubts, you do contact me as soon as possible. And so right now in this video I am discussing about, my dear friends, in this video I am going to discuss about production of silicomanganese. This is yet another very important ferroalloy used in bulk for production of various grades of steel. So let us discuss and get to know about how it is manufactured, what is the silicomanganese, how it is manufactured, how it works. So let's start. To start with, I would like to tell you about the main contents of this video. So it contains first the introduction of silicomanganese, next usage of silicomanganese, then comes methods of silicomanganese production, next comes production process of carbon bearing silicomanganese, next comes abnormal conditions and their troubleshooting, which are based on my extensive operational experiences and practical experiences, and next, last but not the least, burden calculations for 1 metric ton of silicomanganese. This is very important particular aspect, as I will teach you how to calculate the burden for 1 metric ton of silicomanganese, and it is very important. So step by step the burden calculation steps I will be covering in this video. So do watch the video till the end. So let's get into the video presentation for today. So this is the silicomanganese metal which is ready to be ready for selling. This is how it looks. Silicomanganese, it is a bright silvery metal, and it is having a good amount of weight. Specific gravity is very high, and this is the silicomanganese slag. It is also discarded in the form of dumps. So to start with, silicomanganese is widely used in extractive metallurgy as a complex reducer, deoxidizer and an alloying addition in the production of various grades of steel. Moreover, the silicomanganese goes for the production of refined grades of ferromanganese. Silicides of manganese are stabler compounds than manganese carbides, since the heat of formation of manganese silicide from the elements is 14,000 calories, while that of Mn3C, that is manganese carbides is 3600 calories. Therefore, the higher the silicon content in silicomanganese, the lower is its carbon content. The 20% silicomanganese is used for the manufacture of medium carbon ferromanganese, while silicomanganese of 30% silicon is smelted for the manufacture of metallic manganese.
This graph shows the relationship between silicon and carbon in the silicomanganese. As can be seen that the optimum silicon content, that is 16%, carries carbon up to 2.6% maximum.
Silicomanganese can be produced by the following methods. First, reduction of quartzite silica by coke carbon with the addition of manganese into the mixture in the form of carbon ferromanganese. Second, simultaneous reduction of silica and MnO by the coke carbon contained in a mixture composed of quartzite and manganese bearing slag.
My dear friends, just to interrupt you all, here I would like to emphasize on some special important aspect of Knowledge Galaxy. Here specialized subject-wise coaching classes and topic-wise doubts clearing are available. I am available for all of you to clear all your doubts, and especially for Diploma Engineering, Metallurgy and Mechanical students, Indian Institute of Metals, that is IIM, Part 1 and Part 2, and competitive and recruitment exams for GATE, SAIL and various other government and private sector companies, metallurgical industries, working and aspiring professionals. Here I would like to emphasize that whatever queries and doubts you are having in your mind regarding any subject or topic of metallurgy or any other ferroalloy production, operation, maintenance, so you can contact me for getting your doubts cleared. I will try to provide you accurate knowledge and to the best possible extent at the very shortest period of time, so that you can gain your knowledge, clear all your doubts, so that you can grow in your career, whether it is academic career, whether it is professional career, and so that you can develop and grow. So to continue with, here complete syllabus coverage for the students aspiring to appear in the forthcoming semester exams, that is December or June, I will be providing you all. So please contact me on knowledgegalaxy26@gmail.com or WhatsApp me on +91 99 071 44101 for scheduling and organizing the classes or getting informations to clear your doubts via video conferencing, call or WhatsApp. My dear friends, you might have encountered that you might have been having many of the doubts regarding process, technology, why they are doing, why it is done, how it is done. So, and if you don't find any answer to them and nobody is there to guide you properly, so my dear friends, I am here available to guide you all, to make you know and grow, and so that you don't have any doubts related to your process, products, technology, syllabus, and I will make sure that all of your doubts get clarified and you know the topic and subject very well and completely. So again, let's move on.
The second method is more advantageous, as in this case silicomanganese is obtained by the simultaneous reduction of silica and manganese in the same apparatus, and that is more economical also. Reduction from higher oxides to manganese monoxide, that is MNO, proceeds along the same pattern as in the manufacture of carbon bearing ferromanganese. This is the steps which follows how manganese higher oxides are converted into lower oxides. MnO2 transforms to Mn2O3, then it transforms to Mn3O4, and finally Mn3O4 transforms into MnO. Silicomanganese is usually manufactured by a continuous process in closed top or semi-closed top furnaces with deep penetration of the electrodes. The upper layers of the mixture are heated by the escaping gases evolving inside the furnace. The furnace top, therefore, is cooled and losses through radiation in case of closed top furnaces are negligible. Evaporation of manganese is also negligible in case of closed top furnaces. Silicomanganese with 20 to 25% silicon is easily obtained by this method. Difficulties arise when the second method is used for the manufacture of alloys with a higher silicon content, that is above 25%. They are due to the fact that the silicon content in the slag goes up with the increase in the silicon content of the alloy, thus rising the viscosity of the slag and rendering its tapping difficult. It is specified here that these difficulties can be overcome by smelting the alloy in small furnaces with higher slag basicity and by introducing small amounts of fluorspar into the mixture. Silicomanganese is used for the smelting of refined ferromanganese, at present manufactured from a mixture composed of amino-rich slag, quartzite, manganese ores, fine coke and iron chips. The introduction of amino-rich slag into the mixture permits the manufacture of silicomanganese with a minimum phosphorus content. Prior to being used, the amino-rich slag containing 38 to 44% amino and 0.015 to 0.030% phosphorus is crushed into pieces of maximum 50 mm size. Quartzites should contain minimum of 96% SiO2 and maximum of 0.012% phosphorus. It is used in the lumps of sizes not more than 60 mm. Fines of less than 10 mm shall be screened out. The typical composition of the slag of the silicomanganese production should be 16 to 18% amino, 42 to 45% SiO2, 8 to 12% CaO, 11 to 12% Al2O3, 1 to 1.5% FeO and up to 15% MgO. My dear friends, this is very critical information which I just shared with you all. So do remember this very carefully. Moving on, alloy and slag are tapped out simultaneously 3 to 4 times per shift depending upon the liquid metal and slag handling facilities in the tapping bay. Each heat of silicomanganese is analyzed for manganese, silicon, carbon and phosphorus contents. Following solidification after a lapse of 1 to 1.5 hours approximately, the silicomanganese cakes or ingots are extracted from the molds and conveyed to finished products area where they are broken into different sizes, cleared of slag, assembled into batches of similar analysis and then packed in bags and finally dispatched to the customers. All activities in the finished products area are done as per customers' requirements. So now we will be discussing about production of carbon bearing silicomanganese. The production of carbon bearing silicomanganese is a continuous slagging process. The oxides of iron, manganese, silicon, phosphorus, etc. contained in the ore are reduced by coke carbon in smelting carbon bearing silicomanganese in electric arc furnaces. The reduction of these oxides is attended by the evolution of gases at the furnace top. Higher oxides of manganese ores introduced into the furnace decompose with the evolution of oxygen at low temperatures of 430 degrees Celsius. The reaction proceeds accordingly. This 4MnO2 reduces to 2Mn2O3 plus O2. While manganese oxides decomposes at 950 degrees Celsius, according to the reaction, 6Mn2O3 decomposes to 4Mn3O4 plus of O2. Mn3O4 is reduced by carbon monoxide to MnO by the reaction Mn3O4 plus CO is equal to 3MnO plus CO2. Consequently, manganese ore reaches the high temperature zone as MnO. My dear friends, always keep in mind the various steps of manganese ore, higher grades to lower grades decomposition. The reduction of MnO by fixed carbon proceeds at about 1430 degrees Celsius as per the reaction MnO plus C is equal to Mn plus CO. At lower temperatures, the reduction of MnO may be accompanied by the formation of Mn3C as per the reaction 3MnO plus 4C is equal to Mn3C plus 3CO. Mn3C obtained is reverted to the alloy as its melting point is approximately 1250 degrees Celsius. At these temperatures, the conditions for the reduction of silica contained in the manganese ores are unfavorable and a considerable portion of it reverts to the slag along with the oxides of aluminium, calcium and magnesium. Silicates MnO.SiO2 and 2MnO.SiO2 generated in the furnace revert to the slag and hamper the reduction of MnO. A flux, lime or dolomite is added to the mixture to cut manganese slag losses. In this case, MnO is freed from the silicates as per the reaction MnO.SiO2 plus CaO.MgO. This gives to CaO.MgO whole dot SiO2 plus MnO. This way MnO is freed. MnO.SiO2 plus 2CaO.MgO is equal to 2CaO.MgO whole dot SiO2 plus MnO, and it may be reduced by carbon. When smelting carbon bearing silicomanganese, phosphorus pentoxide, that is P2O5, is readily reduced and reverts to the alloy, thus sharply worsening the silicomanganese quality. About 65 to 70% of pore phosphorus is recovered in the alloy. So now we will be briefly discussing about main reactions at various temperature zones in the production of ferromanganese and silicomanganese as follows. My dear friends, as ferromanganese and silicomanganese both are very much related, their reactions and temperature zones are very much similar. So I am just quickly covering this. So the temperature range is 430 degrees Celsius to 1430 degrees Celsius. These reactions are common in ferromanganese and silicomanganese production both. So first reaction is Fe2O3 plus 3C, this gives 2FeO plus 3CO. Next is 2FeO plus 3CO gives 2Fe plus 3CO2. Second reaction is MnO2, it decomposes into Mn2O3, then it decomposes into Mn3O4, then it decomposes into MnO, that is higher oxide of manganese reduces into lower oxide of manganese, and finally MnO is reduced by carbon giving Mn plus CO. Third reaction is SiO2 plus 2C, this gives Si plus 2CO. And next reaction is P2O5 plus 5C, this gives 2P plus 5CO. So my dear friends, let us now discuss about some abnormal conditions and troubleshooting which are very much practical in nature, and I have gained them over my exposure of practical operations exposure over the years. The descent of the charge has a serious effect on the smelting procedure. Therefore, it is necessary to ensure a uniform burden movement over the whole furnace area. This is achieved by timely racking of the charge burden onto the electrodes. For better furnace operation and adequate charge mixing, coke is weighed first, manganese ore second, and then iron chips and fluxes. As soon as the mixture sinks close to the electrodes, new portions of the materials are fed to the furnace. The mixture is conveyed from furnace bins through tubes onto the furnace top. After that, the mixture is heated around the electrodes by racking in the form of cones rising 300 to 400 mm above the furnace top level and up to just below the contact clamps or pads. Normal furnace operation is characterized by the presence of constant charge cones around all electrodes. Following are the benefits of racking the charged materials around the electrodes. My dear friends, many of you might have faced these questions, that what is the benefit of racking charged materials around the electrodes. So I am explaining the benefits of racking the charged materials around the electrodes. Do remember these carefully. First, it ensures uniform evolution of gases over the entire charged surface. Deep and stable positioning of electrodes inside the charge burden means optimum penetration. Collapse-free burden descent means smooth movement of the burden inside the furnace. Maintaining proper permeability in the charge burden inside the furnace enables consistent and hassle-free evolution of gases, resulting in uniform and effectively improved contact of reducing gases with the charge mix, thereby improving the reduction of the charged materials, which in turn results in correspondence of the alloy and slag contents
to the burden calculations. I hope my point is very much clear to you all. Let's move on. Breaks and reduces the formation of bridges, scaffoldings, etc. in the charge mix inside the furnace. This is, I am talking about the racking operation, thereby increasing the effective reaction crucible volume and improving the furnace productivity. It facilitates properly interconnected reaction crucibles of all electrodes, which results in easy tappings and better recovery of alloy and slag. Heat losses are minimized by properly covered electrodes and heat is effectively utilized. The charged materials prevent the atmospheric air from contacting the hot electrodes, which will get eroded if exposed to air and eventually resulting in electrode breakage. My dear friend, so I hope you might have got a very important point why racking of charged materials is important in production of ferromanganese as well as in silicomanganese. If the furnace works normally, the charged materials reaches the high temperature zone well prepared and heated. When the charge hangs onto the electrodes, there is a possibility of collapses with subsequent ejection of red hot mixtures and slag. High temperature below blowouts about 1000 degrees Celsius, which occur simultaneously, may cause the considerable manganese evaporation and breakdown of mechanical and electrical equipments, damage to the furnace timings, surroundings, and that could be fatal also. Therefore, the sintered sections of the furnace top should be poked by iron ravelers or pulls, while the mixture hanging onto the electrodes should be pushed down. Deviation from normal furnace operation may be caused by lack or excess of reducing agent in the charge mixture. In the former case, the alloy has low manganese and silicon and high phosphorus content. The electrodes penetration is excessively deep, power input at the electrodes fluctuates, manganese losses in the slag increases, furnace productivity falls, and specific power consumption rises. Lack of reducers may lead to the damage of furnace linings, especially in the tap hole zone. When a furnace operates with an excess of reducer, heat losses rise, for the electrodes are shallow and evaporation of manganese increases. The silicon content in the alloy goes up. The currents in the electrodes are on the higher side, making it very difficult for the furnace operator to maintain proper load in the furnace. The abnormal conditions in the furnace emerges because of the disturbance in the slag chemistry, electrode penetration, and or water leakages inside the furnace. The remedy also varies depending on the actual causes of the problem. SiO2 content in the slag should be ideally around 42 to 45% and the basicity should be between 0.4 to 0.6. Al2O3 content also plays a vital role in the slag chemistry and it should be in the range of 13 to 20% maximum. If it crosses about 20%, the slag becomes very high melting and doesn't flow out of the furnace. its content in the ore blend should be in the range of 4 to 4.5%. To set the furnace right, raw materials proportioning, that is burden calculation, and the size of the reducers should be checked, and additional amount of reducers charge, and if necessary, coke weight per charge portion may be increased. In this case, the size and weighing accuracy of coke should also be checked, and extra manganese ore should be, if necessary, be charged onto the electrodes. In all cases of furnace trouble, technological procedures at the furnace top should be intensified. In the production of carbon-bearing silicomanganese, slag and metal are tapped out simultaneously through the same tap hole 2 to 3 times per shift. The liquid metal and slag are separated by the skimmer dam block arrangement, where liquid metal and slag get separated from each other due to specific gravity difference. In many places, the liquid metal and slag are tapped in the cast iron molds, where the liquid metal solidifies in the mold itself and the slag overflows to the sand beds for solidification. The tap hole is cleared of slag and following the tapping, and is then packed, that is closed as much as possible with clay mixed with tempering paste buds. An alloy and slag sample is taken to examine the quality and grade of the alloy and slag produced, and it is analyzed for manganese, silicon, sulfur and phosphorus contents in the alloy, and oxides and basicity in the slag. After solidification, but prior to getting too cold, the metal and slag cakes are sent to the finished product yard with the help of EOT cranes for further breaking, sizing, packing and delivery to the customers as per their requirements. My dear friends, here I would like to mention the standard grades of products. Here I am covering both ferromanganese and silicomanganese, domestic as well as export market grades. So I will be just briefly going through this. You can read this as per your convenience by pausing the video. These grades are standard across all companies and internationally accepted, and they may vary according to consumer requirements. Let's move on. Furnace crews should concentrate on bringing down per ton losses of manganese and specific power consumption, as the raw materials and power are the highest cost items in the production of high carbon silicomanganese. It is possible to improve operating results in high carbon silicomanganese smelting by using closed top electric furnaces, which bring down the cost price of the alloy and improve the working conditions of the furnace operators. So my dear friends, now I am going to describe in detail about the burden calculation or material balance. This is very important aspect, as it determines the expertise of the furnaceman, how to control the furnace operation and how to make very good quality material at a minimum operating cost. So let us start. So following steps are adopted for the burden calculation or material balance. Here I will be describing in detail each step very precisely so that you can learn how the burden calculation is done. It starts with taking the final products specifications and raw materials specifications and reverse calculation of the required manganese ore, quartzite, reductants and flux quantities for the production of 1 metric ton of alloy. Let us consider the product specifications as in alloy: manganese 60%, carbon 2.20%, silicon 15%, phosphorus 0.3%, sulfur 0.03% and iron 20%. My dear friends, this is popularly known as 60-15 grade of silicomanganese, where 60 corresponds to manganese percentage and 15 corresponds to silicon percentage in the alloy. This is the most common grade for domestic grade. So I am explaining the burden calculation of it. Now, N slag MNO 13%, FeO 1.5%, SiO2 47%, NGO 8%, CaO 12%, Al2O3 13%. So let us consider the raw material specifications as manganese 35%, Fe 6.4%, phosphorus 0.20%, SiO2 13%, quartz SiO2 96%, Al2O3 1.9%, CaO 0.56%, NGO 0.7% and moisture 8% and moisture in quartz 1%. My dear friends, raw material analysis should be precise and accurate because the whole burden calculation depends on this raw material analysis. The reducer fine coke contains 70% fixed carbon and 14% of SiO2. Dolomite containing 50% CaO plus MgO serves as flux. So let us consider the recovery of each element as follows. Recovery of each element is also very important, as how much percentage we will be getting in alloy, how much will be lost in slag. So we have to always keep in mind for correct and efficient accurate burden calculation. So in metal we get manganese of 82% recovery, recovery of iron is 97%, silicon recovery is 52%, phosphorus 80%, sulfur 8% and carbon 5.5%. In slag we lose manganese 8%, iron 3%, silicon 45% and phosphorus 20%. In gas losses we lose manganese 10%, silicon 3% and sulfur 92% and carbon 94.5%. You have to always keep in mind all the recoveries and losses in mind so that you can calculate the burden very accurately and precisely. The amount of fixed carbon in the mixture exceeds the stoichiometric amount by 25%. Moving on. So let us first calculate required manganese ore for 1 metric ton of alloy. So here comes the calculation. 600 divided by 0.35 into 0.82 into 0.92 is equal to 2272 kg of dry ore. My dear friends, here you might be surprised from where these 600 and other figures came. My dear friends, this 600 corresponds to 60% manganese in ferroalloy silicomanganese grade and 0.35 is the 35% grade of manganese ore. 0.82 is the 82% recovery of manganese in silicomanganese, and 0.92 is 8% moisture minus the dry quantity. So all equation comes to 2272 kg of dry ore. And now taking 2% handling losses, it comes to 2272 into 102%, that is 2% handling losses, comes to 2317 kg of dry ore. So now amount of manganese reduced by the reaction MnO plus C is equal to Mn plus CO. So it gives 2317 into 0.35 into 0.82 into 55 whole divided by 71 is equal to 515 kg. 55 is the atomic weight of manganese and 71 is the atomic weight of MnO, that is manganese plus oxygen, comes to 515 kg. Next is amount of iron reduced by the reaction FeO plus C is equal to Fe plus CO. It comes to 2317 into 0.064 into 0.97 into 56 whole divided by 72. Here 0.064 is 6.4% content of iron in ore. 0.97 is 97% recovery of iron, and 56 is atomic weight of iron. 72 is atomic weight of FeO. It comes to 112 kg. Mn and Fe total comes to 515 plus 112 equal to 627 kg. The manganese and iron content in the alloy, the sum of carbon and silicon is subtracted, averages 100 minus 2.2 plus 15 is equal to 82.8%. The amount of alloy obtained is equal to 627 divided by 0.828 is equal to 757 kg. I hope all these steps are very much clear to you all. Please do watch and remember all these steps very carefully so that you can do a very accurate and efficient burden calculation. Next, moving on. The amount of silicon in it is 757 into 0.15 is equal to 114 kg. This 0.15 is 15% silicon in the alloy. Moving on next, the amount of carbon necessary. So here I am going to describe about how to calculate the required carbon in this. For the reduction of MnO, according to the reaction, MnO plus C is equal to Mn plus CO. Now 515 into 12 divided by 55 is equal to 112 kg. For the reduction of FeO, according to the reaction, FeO plus C is equal to Fe plus CO. It comes to 112 into 12 divided by 56 comes to 24 kg. Next, for the reduction of SiO2, according to the reaction, SiO2 plus 2C is equal to Si plus 2CO. Putting the values here, 114 into 60 by 28 into 24 divided by 28 is equal to 209 kg. For the carbonization of the alloy, 627 into 0.022 is equal to 14 kg. 627 into 0.022 is equal to 14 kg. Next comes total amount of fixed carbon necessary. This is the sum of all total. 112 plus 24 plus 209 plus 14 comes to 359 kg. amount of dry fine coke necessary including 25% excess is equal to 359 into 1.25 divided by 0.7 is equal to 641 kg. 0.7 is 70% fixed carbon of the coke. Next, amount of weight fine coke necessary having 8% moisture is equal to 641 divided by 0.92 is equal to 696 kg. My dear friends, here don't get confused with these two different quantities, as 641 is the dry coke quantity and 696 is the weight fine coke quantity. They are two different and separate quantities. So now let us calculate the necessary amount of quartz. So total amount of SiO2 required for the alloy given by 150 into 60 by 28 whole divided by 0.52 comes to 618 kg. SiO2 introduced with the dry ore is given by 2317 into 0.13 is equal to 301 kg. SiO2 introduced with the dry coke is given by 641 into 0.14 is equal to 90 kg. So that total SiO2 required to be provided by quartz is given by 618 minus 301 minus 90 comes to 227 kg. So required quantity of quartz can be calculated by 227 divided by 0.96 into 0.99 into 28 by 60 is equal to 111 kg. So let us now calculate the necessary amount of dolomite, X being the amount of dolomite introduced with the dry ore. It comes to SiO2, it gives 2317 into 0.13 is equal to 301 kg. Al2O3 2317 into 0.019 is equal to 44 kg. NGO 2317 into 0.007 is equal to 16 kg. CaO 2317 into 0.0056 is equal to 13 kg. So total CaO plus NGO is equal to 29 plus 0.5x kg. SiO2 plus Al2O3 plus CaO plus NGO sum of total is equal to 301 plus 44 plus 29 plus 0.5x is equal to 345 plus 29 plus 0.5x is equal to 374 plus 0.5x kg. So 374 plus 0.5x is equal to 0.2 into 29 plus 0.5x. Here 0.2 is 20% in slag. Equation comes to 374 plus 0.5x is equal to 0.2 into 29 plus 0.2 into 0.5x. I am just simplifying the calculations. 374 divided by 5.8 is equal to 0.5x minus 0.1x. So x is equal to 64 divided by 0.4 is equal to 160 kg. Thus, the composition of dry mixture for the smelting of 1 metric ton of silicomanganese will be as follows. So, we have calculated all the quantities. So, here are the quantities. Manganese ore 2317 kg, fine coke 641 kg, quartz 111 kg, and dolomite 160 kg. I hope this calculation is very much clear to you all, and I have covered all the calculation of each element very precisely, so you can learn it Barton calculation very accurately and precisely.
Dear friends, I am providing you all the informations free of cost which are available in my YouTube channel. So do help me by watching all my videos. Do subscribe my channel. Regularly visit and repeatedly visit my channel. Do watch all my videos, contents, like the content, share with your friends, and so that I also get motivated from each one of you as you subscribe to my channel. I am very much thankful to all my subscribers who believe in me, have subscribed my channel, and like my content. So to motivate me further, please do subscribe my channel, increase the subscriber count, share with your friends so that others can also gain the knowledge. And my dear friends, all if you subscribe my channel, this will motivate me to do further better. So I hope you like the content and found the video worth. So again request you to please don't forget to like, share and subscribe the channel. Also remember to press the bell icon so that you can get the notification of the new videos promptly. My dear friends, here if you want to advertise about your product, services or company or anything else for gaining popularity in my channel, so you can contact me so that I can put your content for advertisement in my videos, forthcoming videos. So it will be a good platform to advertise. So do contact me as soon as possible. Thank you very much for watching this video till the end, and I am very much again thankful to all of you who helped me, who believe in me, and please do visit my channel regularly and repeatedly. Thank you very much again. See you in the next video. Thank you.